Good morning, doctor. So today we are group one and we would like to present our project on the arithmetic logic unit design. So right now I'll briefly explain what is the ALU. So it is basically a computing component used for graphic processing and central processing units. And it involves AND gate, OR gate, XOR gate, and other numerous operators. So without further ado, let's move on to explaining how to design the ALU. Alright, so in order to design our ALU, first things first, we design our multiplexer. So as you can see, this is our block diagram of our multiplexer as shown in the Quartus app. So this is a block diagram and it is a 4 bits 4 to 1 multiplexer. We use 4 1-bit 4 to 1 multiplexers where they all share the same selectors, which is S1 and S0. So when uh, our selector is 1, the input A0, A1, A2, and A3 will be chosen from each multiplexer, where the MSB is the A31 and the A01 is the LSB. So therefore, we will get A31, A21, A11, and A01 as our input to our adder and subtractor. So both A and B use the same design of the 4-bit multiplexers. And right now, Junxiang will talk about the adder and subtractor part.
Okay, now I'm going to talk about the block diagram of adder and subtractor. After the values of A and B obtained from the multiplexer, it will be used as the inputs for adder and subtractor. So we use ripple carry adder to perform the adder and subtractor part block diagram. As example, when both numbers A and B are selected from the multiplexer, the input of B and C0 will be connected to the XOR gate with C0, which C0 is the initial carry and also the ALU OP. So when the value of C0 is 0, it performs as an adder since B XOR 0 equal to B. Thus, it will carry out the equation A plus B. In the other hand, when C0 is 1, it performs as a subtractor since B XOR 1 equal to B. Therefore, it will carry out the equation S equal to A minus B. So after the operation all is done, we will get the output value of S0, S1, S2, and S3, and they will be connected to the D flip-flop after that. So now I'm going to talk about the D flip-flop part. So for this case, D flip-flop it acts as a register. There are 4 bits, so we use 4 1-bit D flip-flop to operate. The output of the adder or subtractor will connect to the D input for each flip-flop. So in this part, we also need a clock to make the connection successfully. Finally, the output of each flip-flop will be our final answer, which is the value of the output ALU out will also be Q0, Q1, Q2, and Q3, which Q0 is LSB and Q3 is MSB. Now I'm going to pass to Eric to talk about the waveform simulation results in Quartus Prime.
Okay, thank you, Junxiang, for the explanation. So for the waveform part, actually, if we use the Quartus app to perform each waveform simulation, it will take a lot of time and sometimes there's error when running. So instead, we'll just present and summarize it in the form of this document. So as you can see, this is our waveform simulation results and This is the simulation of the 1-bit full adder, and it proves that it works just as intended. So, and this is our multiplexer, and the functionality is verified. Once our marks is done, and we can move on to our complete circuit. And this is our complete ALU circuit design. Right, so for example, I can talk on this, and when A is 10, then AG is 1000, and B is 00. So BG is 010. So in this case, our ALU op is equal to 1. When it is equals to 1, subtraction will proceed. So we'll just take the 1000 minus 0101, we'll get 0011. And thus, as you can see, our output is the same as in the waveform simulation. So this clearly shows our design works and it is verified. So right now I'll show the complete design of our ALU in Quartus Prime. So this is our ALU design, which consists of our marks, our adder and subtractor. So right now, in conclusion, our group has successfully designed a 4-bit ALU design, and it follows the open source regularity and simplicity of the RISC-V. So that's all from our group. Thank you.